Thank you very much, Paolo. Good afternoon, everyone. I'm going to talk to you this afternoon about the sulfur emission control area in the North Sea and Baltic. My name is Robert Yates. I'm from AF Consult, which is a consulting and engineering group, 7,500 staff operating out of 26 countries. I have 4 divisions working in LNG, gas engineering practice, gas economics, gas markets, and we have an LNG transactions practice working in the buying and selling of LNG cargoes. We have a number of projects in LNG. There is one that we have undertaken that is of particular interest, I think, to yourselves today. This was the North European LNG infrastructure project, essentially a feasibility study for a network of LNG filling stations around the North European seas. This was a project that was co-financed by the European Union and by the Danish Maritime Authority. The full report is available on the Danish Maritime Agency website. You probably can't see the web address there, but these slides are being handed out afterwards. So anybody interested will be able to access the report and its numerous appendices later on. That report covered all aspects of creating an LNG filling station, bunkering station network. So it looked at all of the technical aspects, both of the shipping and of the ports and harbours. It looked at the safety dimensions. It looked at the legal and the regulatory requirements. It looked at the fuel qualities, the metrology, that is the measuring of the quantities of fuel, and a lot of extensive work on the finance and the economics and the supply of LNG. So I think that should be a study that is of great relevance to the situation here in Italy at the moment. Okay, I've just got a few slides on the general introduction. The sulfur emission control area for Northern Europe covers the English Channel, the North Sea, the Baltic, and the Skagerrak, which is the sea area between Sweden and Denmark. This area has been operating under an emission control for shipping of 1% as a maximum allowable sulfur content in the bunker fuel. On the 1st of January 2015, that is due to change to be 0.1% as a sulfur content of bunker fuels. The volume of shipping coming into the area, as you might imagine, is significant, and just schematically gives you a rough idea of the cargoes that we're dealing with, the volume of shipping, and the number of ports. On that slide, I show you the principal ports within the region, but on our database, when we were doing the network development analysis, I think we were working with around 350. In terms of volume of shipping, we have, of a global fleet in 2000, I think this is 2010 data, of a global fleet of 106,000 ships which are registered on the AIS shipping system. Around 14,000 come in and out of that SECA region. Some of those operate within the region 100%. Some of them just come in and out. Probably international shipping will just come in and out to deliver to the North European ports and exit again. On this slide, I've got data on the volume of shipping, 14,000 vessels in total, average tonnage of 862, which I think is, that'll be annual fuel consumption in tons per ship. and the proportion or the numbers that operate 100% in the region and just above 50, below 50 and less than 25. And we've broken down the Seeker region into its 4 areas. Just briefly to look at that from the ship owner's perspective, what that change in the sulphur emission regulation might imply. If you're a ship owner, what are you going to do? If you've got an existing ship, you've got 3 strategies. You can swap across and use marine gas oil, which is a low sulphur product. It is relatively expensive, which I will show you in a moment. The costs of conversion are quite small, but MGO is an expensive fuel. The volume at the European refineries is also quite small, so if a number of ship owners were to adopt this strategy and swap across to MGO, we would expect that the price would move significantly. If your ship is currently using HFO, heavy fuel oil, as most of them are, then you've got the option of fitting a scrubber, and that has some capex cost, not huge. There is an unknown in the sense of disposing of the products of the scrubber. So lower OPEX, but slightly higher capex than the marine gas oil version. You can retrofit LNG. This has quite high capital costs, but you then benefit from the very low cost of LNG as a fuel. So it has low OPEX. It will give you an OPEX saving, but quite significant capital costs. Retrofitting ships, we got on our database categorization by types of shipping, by size and by age. And the strategy that the ship owner might adopt will differ depending on the age of the ship and the ease of retrofitting. For example, a container ship, it is possible to replace a couple of the containers with containerized LNG storage tanks. So retrofitting that storage is not a huge engineering problem. If you're looking at a fishing boat, then finding capacity to locate the storage tanks is a much more significant engineering problem. If you've got a roll-on, roll-off ferry, there are solutions being promulgated where we've seen truck solutions to transporting LNG. It's quite possible to load a couple of those trucks onto a ferry and use them as the storage for your fuel. So the options such as that, which bring down the capex, are being explored. We do expect a much more significant penetration with new builds where the engineering problems are much smaller. I've mentioned payback times for the ship owners. I'll come back to that in a second. If I can turn first just to look at the actual fuel price. On this graph, I've got the historical prices of the 3 main fuels, shipping fuels, as at Rotterdam. I don't know if you can see the graph clearly, but the green line is marine gas oil, MGO. The light blue line is heavy fuel oil. The purple line is LNG, and I've got the price of Brent crude in red as a reference. If I convert that graph into relative prices, you can see the picture more clearly. These are the relative prices of LNG and MGO to HFO. And as you can probably see, by 2011, LNG is roughly 50-60% of the price of HFO, whereas MGO is roughly 1.5 times the price. So if your ship can be converted to LNG, you've got a significant potential fuel saving. I'm sorry if this particular table is not easy to see, but I'm sure it will get the message across. We have looked at 4 basic types of vessel, roll-on, roll-off ferry, a coastal tanker, a container ship, and a fishing boat. We have looked at different price scenarios, which are described down the left-hand column as low, central, and high. And we've looked at the payback times that a ship owner might get. And without going into any great detail, you'll see that for the large part, payback times are 2 to 3 years, 3 to 4 years. So quite a lucrative investment for the ship owners, even without the emission control requirement. This is a potential saving. As an economist, I'm not hugely comfortable in quoting payback times to you, but a number of shipping companies collaborated in our project, and they were quite insistent that all their proprietors dealt in payback times. So that's why it's presented that way. If I can just touch briefly on what that might mean for demand for LNG around the Sika region. In the report, you'll find a whole chapter devoted to this. This is just one graph extracted from it. It shows demand in 2015, 2020 and 2030 broken down between vessels retrofitting and new build vessels, but shows a potential demand 7 million tonnes per annum for LNG from shipping in the Sika region by 2030. And just as a reference, total fuel demand in the Sika region, including international shipping, bunkering in northeastern Europe, is around 36 million tonnes per annum at the moment. If I can turn quickly to look at actual LNG bunkering. This is not behaving. Okay. This is the European gas grid at the moment, and I can just draw your attention that in Norway, Sweden, and much of northern and western Finland, there is no gas grid, and that mirrors the position in the Western Balkans and in Sardinia. And that creates an additional demand for gas, a potential additional demand for gas. This is interesting. This is the existing LNG infrastructure in Northern Europe. Again, you might want to look at this afterwards in a little more leisure. We've got about 12 major import terminals in northeastern Europe. Rotterdam, Zeebrugge, Dragon, Hook, Teesside, and so on. These are all feeding national gas grids, national gas networks. What will have caught your eye immediately is a host of smaller LNG terminals around the coast of Norway, where there has been active government intervention and subsidy to promote the use of LNG. They don't have a national gas grid network. They do have plenty of gas, and there has been a positive financial and fiscal incentive to develop small LNG terminals around the coast, which then use trucks to feed local industry and commerce, as well as fueling the shipping fleet. Very briefly, the marine supply chain. I think we're probably a little bit tight for time, so I won't go through that in great detail. Let's move on to what it might mean for the bunkering for shipping. And you've got a number of possible solutions. You've got the major international LNG cargo carriers and the possibility at those major points to have a transshipment point into smaller vessels. And as I think one of the earlier speakers mentioned, there is a facility under construction at Rotterdam for that nature of transshipment, and another in northeastern Germany under construction. With the LNG loaded into a smaller vessel, you then have two possibilities. One is that you can do ship-to-ship bunkering, either in harbour or out of harbour, or that smaller vessel can deliver to import storage facilities, which can then support transshipment to a smaller vessel or to trucks, which can then go on to even smaller ports and tranship that way. That slide just expands one part of that previous slide on the possibilities. And picture of ship-to-ship bunkering, and that is a small coastal LNG ship, and you can see there that we've got an LNG bunker vessel feeding a shore-based facility, which is also being unloaded to a truck. If I can turn now to examples of some specific ports and what the economics of those might look like. And we've looked at 3 example ports and what the economics might look like. The large port case that we looked at was taking one of the major LNG import terminals and looking at the technical and cost implications of constructing the transshipment facility. So we're assuming that that port has already got LNG storage, and what the transshipment facility would require is probably a separate jetty and then reloading facilities for the LNG, but probably not any additional storage. In a medium port case, the example we took was 20,000 cubic meters of storage. We coupled in with that 2 bunkering vessels and an LNG truck filling station. And then a small port case, which would have 2 700 cubic meter storage tanks and 1 truck filling station and 1 truck. And we associated annual throughputs with each of those. On this slide, you've got indicative capital costs for each of those example projects. And we've broken down that capital cost between what is invested in the bunker vessels as well as the total investment cost. And we've also analysed what the operating costs might be. We translated that into what that might imply into a handling cost per tonne for the LNG. And the figures range quite widely for the small and the large. Typically, we were coming out with a sort of average of about 170 euros per tonne as a handling cost, materially higher for the small port, significantly lower for the larger port. One of the problems that is a little bit of an unknown at the moment is actually sourcing the LNG. Cargoes of LNG come into Europe mainly under long-term contracts, probably being fed straight into national gas grids and are therefore under contract either to one of the major international oil companies, one of the national gas companies, or some joint venture between the two. And trying to secure long-term, smaller volumes of LNG is one of the areas that is proving a difficulty for everybody that is trying to develop smaller scale LNG. Our take on this was that in the short term, it would be rational for ports like Rotterdam building a transshipment facility, and they will own the gas at that point, that they will probably price that gas not a long way below the price of marine gas oil. And it will take a little while for competition to develop and the cost of LNG coming down to a more cost-reflective level. We went on just to look at, sorry, okay, 5 minutes. I've just been told 5 minutes, so I'll press on. LNG demand from ships sailing outside SECA. We had concentrated on ships sailing within the sulfur emission control area. There's a potential additional demand from what I call long-haul shipping, particularly as other countries and other regions of the world develop sulfur emission control areas of their own. We've got it in the US, it's under discussion in the Far East, and the IMO are developing their own regulations. Right, finally, just to look briefly at the particular economic case for individual ports. On this graph, the port case 1 is the large port, port case 2 is the medium port, and port case 3, am I doing that the right way around? Yes, port case 3 is the small port. And this is just looking at the potential internal rates of return for different volumes of throughput in tonnage. And the conclusion of that was that significant volumes were needed to get anywhere near IRRs that could be financed commercially. And this is going to pose a significant problem to get any LNG filling station network started. And I think there was a nice slide earlier on that termed it as chicken and egg, and that's exactly the problem that is here, that probably without some government intervention, it's going to be difficult to get an initial network started across all of Northern Europe. The breakpoints on this graph that are showing the effect of throughput on the cost per tonne of distribution, we're using those 3 example ports again, and these are incremental points where either another bunker vessel or another storage tank is required, and that causes the discontinuities in the graph. What will change the situation in the Baltic area in particular is the potential for land-based demand, and that does change the economics for quite a lot of ports around the Baltic region because they've got this additional customer base. And that could be quite a significant additional demand. I'm going to jump now to one last slide. We did do a lot of modelling work just to look at how the network might develop. We saw that, in fact, there might be as well as the large ports converting to transshipment, and the economics for them are very, very straightforward. We saw a number of small ports developing, helped by this land-based demand in northern Scandinavia. But we saw that a number of the economics for a large number of bunker vessels was attractive, that they provide a very flexible resource, and they can either act as fuel barges within harbours or provide ship-to-ship refuelling, and their economics are quite strong up to a range of 300 kilometres. I will stop there. Thank you very much. Thank you.